And another problem I want to talk about now, I do have time, let me just get this out of the way really quick. So you guys, when we look at this, they're really saying they're gonna dot on number B, part B, or part C. They're saying when they dot the R, that's really what they're saying. And F could be multiple things for you to get X, Y, Z, right? So it has to be anything here, it makes no difference. Anything here, it makes no difference. That means only the K component survives. That must be the X, Y, Z. And that's how they get that. Now again, I'll point that more as we do problems. For now, I want to find work. Officially, it says, find the work done by F over the curve along this path. Well, work is the integral of F dot dr along this curve C. Well, nothing new. 0 to 2 pi. What I need to do, I need to figure out what F is. Depending on the curve, be careful, that's Y. So that's twice the sine of t. That is 3 the cosine of t. And x plus y, that is cosine of t plus sine of t. And now when I say f, well, I mean this f, twice the sine of t, as a function of t, dependent on the actual curve r. Dot it with, and I need to take dr. What's dr? dr will be negative the sine of t, cosine of t, and 1 over 6 with respect to t, and there it is. That's simply the integral from 0 to 2 pi, negative twice the sine squared of t, plus 3 the cosine squared of t, plus 1/6 the sine of t dt. And we know how to do this. Power reduction, and there it is. And we could do that as a practice. I made a mistake on the last part, I'm sorry. When I take this multiplied by 1/6, that's 1/6 into the cosine of t plus 1/6 the sine of t. That's what I meant. And if you play this along, you should get at the end an answer of pi. Okay, and now we're going to talk about a few more things. One, you really don't need to spend much time on this, but these terms do come up, simple and closed. A curve is, in the xy plane, is simple if it does not cross itself. So this right there is simple because it doesn't cross itself. This is simple, it doesn't cross itself. This is not simple, and this is not simple. And you know what closed means? Closed means when the beginning and the ending point are the same. Now, few things to really look at. Vector fields could have many different applications. Among those, the two we're going to be looking at the most are disbursement versus circulation. So you could have a gravitational attraction in which everything is attracted to one point, right? Like Earth, for example, you know, the gravity is sucking everything around it. And when we're going to do work, we're going to look at different different measurements of the vector field. We're going to have one specific integral to figure out whether we're dispersing. So if we're looking for circulation on 16.12, that will be 0. And another integral that will figure out rotation. If you look for disbursement here, it's going to be 0. You know, like gas disperses in every direction. We have a definition that says if R of t is a parametric region of a smooth curve in the domain of a continuous vector field, if I take the starting point to be R of A, that point, and R of B, I set that to be the terminal point, right? This is called flow. The integral is called flow integral, and it's basically what we've been doing up till now. Nothing different. There's one catch. If the curve starts and ends at the same point, then we say this flow is circular. If this happened to begin and terminate at the same point. And I'll do an example on that in a minute. And the last definition we have is the definition of flux. So the top is really work. We did that already. That is really the integral along C of f dot dr. Nothing more. We played with that enough. But this one, calculating a flux across a smooth closed plane curve, flux of f, which is given by mn, across C, and C is defined by x and y. The flux is defined around the closed interval. It has to be closed, C, with the following formula. The integral can be evaluated from any smooth parametric equation that traces C counterclockwise, positive rotation, exactly once. I want to elaborate on what this is. This is equivalent to the closed integral along C oriented of f crossed with dr. So work is f dot dr, flux is f crossed with dr. So if I take f and I say that is mn, and I take dr, if r is xy, wouldn't this be dx dy? And if I take f and cross it with dr, we normally do a cross product on 3D, not on 2D, so we could make that 3D with ease, if you really want, right? Or you could just say, you know what, it's a 2 by 2, and that would be m dy minus m dx. That would be much easier for the way we're going to do things. I am going to take definitions from this book, because those are not as simple to make up, but I am going to elaborate on how we're going to be using those. So I want work f dot dr, I want flux f crossed dr. Number 30, it says find the flux of the vector fields across this circle. Well, let me take f1. If I want to figure out the flux along f1, I'm going to say that's the integral along C of the cross product of those two. I did put, I forgot about that. I'm sorry. It's right there. Now it's official. Okay. And how does that work? Well, I need to prep this. I need to go ahead and say, well, let's see. If I take f1, f1 is actually twice a cosine of t and negative 3a the sine of t. You see how I'm getting that, right? And dr is simply negative a the sine of t and a the cosine of t. And this is simply the integral from 0 to 2 pi of, let me do that here. If I take twice a the cosine of t, negative 3a the sine of t, and negative a the sine of t and a the cosine of t, that would be twice a squared cosine squared of t minus 3a squared the sine squared of t dt. And that would be the integral of twice a squared, the integral from 0 to 2 pi of cosine squared of t dt minus 3a squared, the integral of the sine squared of t dt, 0 to 2 pi, right? And that turns out to be negative pi a squared at the end. Remember, you're going to use power reduction. I'm trying to set up one more problem if I could, besides this one. That would be great. And if I go across flux of f2, I do have to go in and set it up as well. I'm going to say, well, f2 is actually based on our r. It is twice a the cosine of t, and the j is going to be a the cosine of t minus a the sine of t, and dr doesn't change, it's the same. dr is still negative a the sine of t, a cosine of t, and if I take that would be the integral, it's still 0 to 2 pi, and I need to take f2 crossed with dr, and that would be the integral from 0 to 2 pi, and let's do that. That would be f2 twice a the cosine of t, a cosine of t minus a sine of t. Okay, you know what? I can't finish another one. I can't finish another one. And that's going to be a, what was it? The cosine of t minus a the sine of t, and this would be negative a sine of t, a cosine of t, and if I take those, that will be twice a squared cosine squared of t minus, so it's going to be plus a the sine of t times a the cosine of t minus a sine of t, and there it is. Basically, you just work that out, and this turns out to be pi a squared. I'll try and set up one more. Okay, on number 36, find the flux across a triangle. This is the triangle running from 1, 0, there's 1, 0, to 0, 1 in that direction, to negative 1, 0 in that direction, then back, right? So the flux is going to be the flux around x1 plus the flux around 2 plus the flux around 3. So that's like, you know, C1, C2, C3. Simply, it is those three integrals added. I want to do one of them. I want to work out this first integral, and this is how I do it. If I'm going to run from those, either use the formula that I provided at the beginning of this section at the very, very top, or was it the previous section? I'm sorry, the previous section. Or you say, you know what, this is y equal negative x plus 1. So very simple. For C1, I know that R1 is, I'm going to let this be t, and this will be 1 minus t. And t will vary from, I want to start on the right, from 1 to 0. You could do that. At 1, you are right there. So again, since I chose this to be the t, those are the values I choose. You could do this any way you want. You could say r equal 1 minus tt, and let t run between 0 and 1. There are so many ways you could do this. Bottom line, if I stick, okay, this is what the book does. If I stick with this, this is fine. It doesn't really matter how you do this. I'm going to have to figure out what f is. F is actually x plus y, 1 minus t plus t, and x squared plus y squared. So I'm getting f to be 1, and that is 1 minus 2t plus t squared plus t squared. That's negative 1 plus 2t minus 2t squared. There we go. And now I'm going to say the flux is going to equal around C1, the integral, from 0 to 1 if I chose this, or from 1 to 0 if I chose that. But here, I already used this for my function, for my vector field. I'm going to take f crossed with dr, and that's going to be the integral from 0 to 1, and this is going to be, let's see, f1 negative 1 plus 2t minus 2t squared, and the derivative of this is going to be negative 1, 1, and that would be simply 1 minus plus, because that's a negative, negative 1 plus 2t minus 2t squared dt, and those cancel out, and that's simply t squared minus 2t cubed over 3 evaluated from 0 to 1. So that is 1 minus 2 thirds. That's 1 third. and you find the other two and you add them, and that's how this works. And there's the homework.